All right, so we've talked about modeling mechanical systems, and these are your mass spring damper systems or your rotational inertia. And we talked about electrical systems, where we did mesh analysis, nodal analysis, and we looked at the method of impedance for both of these systems, impedance analysis. And so today we're going to combine these and we're going to talk about electromechanical systems. And as a way of introducing this, we're going to talk about the DC motor. Okay. Everybody is pretty familiar with the DC motor. It's basically, it's an electromechanical device where you apply a voltage and you get out a displacement or a speed. The motor itself is pretty simple, but we'll talk about the armature controlled DC servo motor. And it's really the DC motor. It's only a servo when we measure the position and close the loop on the position. The way that these motors work is that we have a permanent field, a permanent magnetic field. So we have a permanent magnetic field. We usually use B to represent the field strength. And this field is induced typically by permanent magnets. Okay, in some cases it could be electromagnets, so we'll just say it can also be an electromagnet. There's lots of motor designs. And the armature, okay, which is the rotating part of the motor. The armature is just essentially a circuit with lots of wire wound in a coil. And the armature, so it's run in a coil that rotates freely about a shaft. We'll draw a picture here in a second, but we'll talk about the dynamics here. So when current flows, into the armature, it causes a force due to the magnetic field B according to the Lorentz force law. And this force is the current in the armature times the length of the wire times the field. Okay. And what happens is this force, the Lorentz force, we'll just say this force, F, causes a torque on the motor, which causes it to rotate. Okay. When the motor rotates, it generates a voltage. So as the motor rotates, it generates voltage. At the conductor terminals, that would be where you would connect to the motor. Okay, and this voltage V is V, which is the field, times the length, times the velocity of the motor. Okay, so V is the voltage that's generated as it rotates. B is the magnetic field. L is the length of the conductor or the coil in the motor, and then V is the velocity of the motor. And that's the velocity of the motor that's normal to the magnetic field. Okay, so these are the governing equations, and they're sufficient for us to start to model. Okay, so what we can do is we can model this voltage, and we call this voltage, this is the back EMF, or the back electromotive force, or we just call it the back EMF. Okay, and this is the voltage that's generated as the motor rotates, and it actually is a voltage that has to be overcome when we start the motor. So we can model this just as the back EMF, or the voltage, the voltage generated at the terminals, which is our back EMF. And the back EMF is equal to KB, and KB essentially is a function of these terms, but we just call it KB, and this is our back EMF constant. And in some motor manufacturers, or some terminology, they'll use the 1 over KB and they'll call it the velocity constant, but for now we'll just call it the back EMF constant, and it's equal to that times the shaft speed theta dot of t. And what we can do is take the Laplace transform of this. So we'll take the Laplace transform of this, and we just get that, VB of S is just equal to KB S theta of the motor, which is a function of S. So there's our back EMF constant. We already know how to model the dynamics of the circuit, so let's just do that. Okay. So if we have a circuit here, which represents the motor, so this is where you would connect to the armature, and inside of the motor we have the coil. The coil of the motor has some resistance, RA, which we'll call the resistance of the armature. It has some inductance, usually it's really small, we'll talk more about that. We'll call this the inductance of the armature. And then it comes down here, and this is showing the motor diagram, which in this case we're showing the brushes of the motor. Okay, and this voltage here is the voltage in the armature. It's the potential of the armature. This causes a current to flow through the armature, which we'll call IA. And we have this output of the motor, and this output of the motor is applies some torque and some change in position. And we also have the field, which we can just say is somewhere out here, and this is our fixed field, and this is due to the permanent magnet. So this is the motor model, and we know how to model the circuit just by going through KVL. If we do that, we get that the resistance in the motor times the current, which we'll call IA of S. That's the voltage drop from here to here, plus the inductance, and the equation is L di dt, so we just say LS IA of S plus VB of S equals EA of S. And so this first term is the voltage drop from here to here. The second term is the voltage drop from here to here. And this third term is our back EMF. And the back EMF is actually a voltage that's produced here as the motor rotates, and it actually opposes the applied voltage. So this gives us our motor equation, and we know through other ways of modeling or experience, we can say that the torque in the motor is, and notice we're just going ahead and doing this in the Laplace domain, is KT times IA of S. And what we're saying here is that the torque output from a DC motor is proportional to the current. And this term here, KT, is what we call our torque constant. Okay, so KT is our torque constant for that motor. And it's worth noting that you can get KT, your torque constant of the motor, and KB, your back EMF constant, or 1 over KB, which is KV, which is your velocity constant, from the motor manufacturers. Okay. Now, right now we have a way of introducing our torque into this equation because we have an expression for IA. So we can just say that IA of S is equal to Tm of S over KT, and plug it into these equations so that we can get our torque dynamics into the motor equation. If we do that, we get RA times Tm of S over KT plus LS Tm of S over, KT plus KB S theta M of S is equal to EA of S. And note that we can also model our torque using our mechanical modeling for our torque equations. Okay, so if we have some shaft here, and we have the torque from the motor. We have the position of the motor changing. We have the inertia, polar inertia of the motor, and we have some damping because we have bearings. And we call this dm. We could also write the motor torque is equal to, just from Newton's laws, Jm s squared theta m of s plus dm, which is our damping, s times theta m of s. Okay, so now we have the dynamics of the complete electromechanical system, and we can rewrite the terms from this equation. We'll just collect terms, and we'll just say Ra plus Ls over Kt times Tm, but instead of this Tm, we can put our dynamics in from our shaft. We can say Jm s squared plus dm s theta m of s plus kb s theta m of s is equal to Ea of s. Okay, so that's how we included the circuit and the electrical dynamics and the motor dynamics. Now, typically, our inductance is really low, so we say that the inductance is approximately equal to 0. So then the Ls over Kt term is approximately equal to 0. And when we do that, we can simplify the equation a little bit, and we can just say that the motor dynamics are just Ra over Kt times Jm s squared plus dm s plus kb s theta m of s is equal to Ea of s. Or we can say our transfer function between the input and the output, theta m of s, output over input, Ea of s, gives us this expression, Kt over Ra Jm over s times s plus 1 over Jm times dm plus Kt Kb over Ra. Okay, so this is our motor dynamics equation, and this captures the dynamics of the circuit and the dynamics of the motor for this electromechanical system. And so, just like we've done before, instead of using Jm and dm here, okay, so this is, instead of using Jm and dm in these equations, we can also replace Jm and dm with Je, the equivalent inertia, and De, the equivalent damping, if we have something connected to the motor. Okay, so far this describes the motor dynamics itself without anything attached. Okay, but obviously we attach things to the motor so that we can control it, and as we've seen before, we can model what's on the other end of the motor. Okay, so if this is our motor and we have our shaft here, often these motors are connected with gears. Okay, let's just model these things as gears. And this can come into a motor that has, or an output shaft and load, which call this the JL, which would be the load. And this will be the number of teeth on the first gear. This is the number of teeth on the second gear. This is our inertia for our motor, and our damping for the motor that's in there. That's our JM and DM from these equations here. And then we can also have the damping here due to the whatever friction is on the output shaft. And we showed before that we can reflect the torque. So we can reflect the inertia and damping and stiffness if it's there. And the way that we do that is we use the gear ratio, and the gear ratio for the reflected torque will be the number of teeth on the destination shaft over the number of teeth on the source shaft. And this quantity is squared, and we derived that previously. So what we can do is we can come up with an expression, equivalent expression of the torque, and we can say that the torque seen by the motor, okay, so this would be, in this case, our destination shaft is here. So this is our destination shaft, and this is our source shaft. We can say that the torque seen by the motor is then equal to the inertia here, okay, which is the armature inertia, JA, and this is just JA S squared plus DMS. That's the dynamics just from the motor, and then we'll add the JL, which is the load shaft, S squared times the number of teeth on the destination shaft over the number of teeth on the source shaft squared. And we'll do the same thing for the damping, where this is our damping, DL, S N1 over N2 quantity squared, and this is all theta M of S. And so we can collect these terms and call these equivalent motor dynamics. And so we can collect this term with this term and this term with this term. We can say that the torque on the motor is equal to JA plus JL N1 over N squared squared times S squared plus DM plus DL N1 over N2 quantity squared S theta M of S. Okay, and so that's how we include the additional components of the shaft. And what we can call this is, we can just call this our equivalent polar inertia for that shaft, and we can call this our equivalent damping. And then we just have the motor equation. Tm is Je s squared plus De s theta m of s. Okay. All right. So we've seen how we model the electromechanical system and model the load that's attached to it. So the question is then, how do we get these motor constants? Since typically the motor constants are given to us, but we'll just say, you know, how do we get KT and KB? And you can look these up for a motor, and you can pull them off the data sheet, the units, maybe in different terms, or KB may be 1 over KB, which is the velocity constant. Here we're using a back EMF constant, but you can get these from typically from motor data sheets. Okay, so we saw before that our motor model was, if the inductance was small, was just RA over KT times Tm of S plus KBS theta m of S, and that was equal to the voltage on the armature current. And so if we put these back in time, we can just say RA over KT. So if we take the inverse Laplace transform of these and put this back in terms of time, then KB theta, instead of theta m, we're going to use, we'll call this omega of the motor. T is equal to EA of T. And we'll look at this at steady state. Okay, so at steady state, Tm of T, the motor torque, is just equal to Tm, and the omega m of T at steady state, it will just be the constant speed of the motor, and the applied voltage as a function of time will just be EA. And these are all constants. Okay, so we can take a look at this at steady state. At steady state, we just write that the voltage is equal to RA over KT times Tm plus KB times omega m. So we can use this relationship, and we can supply different voltages and then measure the speed. So what we do is use this relationship and then do experimentation by applying different voltages and measuring the speed. Okay, so when the speed is 0, then we can get a relationship here. Okay, so when omega m is equal to 0, then that allows us to get an expression here for KT with an applied torque. Okay, and that's what we call our stall torque. And what this looks like graphically is where we have on this axis the torque, and then on this axis we have the speed. So for a given voltage, let's say we have this is our torque, then we have this relationship here. So this might be like EA1, and at this point right here, and this is our speed, at this point here, this is what we call our stall torque. Okay, so if we apply a torque enough torque such that we get zero speed, then this is the stall torque. Okay, and in this case, when there's zero speed, we just say EA is equal to RA over KT times TM. When there's no load, here we have a zero load, and we can increase the speed, and we can get our max speed for this voltage. Then that's how we get our EMF constant, because in that case, over here, Tm is equal to 0, and this is called our no load speed, and we can get an expression there that just says Kb is equal to the applied voltage over omega NL, and that's this point here. This is your omega no load speed, and that's how we find the torque constants and the back EMF constants through experimentation. And like I said, you can look these values up for different motors. Okay, so let's look at an example with some numbers here. Okay, so let's say we have this motor, and we're ignoring the inductance of the armature. We're saying that it's approximately equal to 0. And we have this applied voltage here, EA. We have the resistance, RA. We have our back EMF, VB. And we have this shaft. And let's say that this shaft is connected to a gearbox in 1 to N2, like we saw before. And we have this connected to another shaft, which might be a gearbox with a load. Call this JL, and it has some damping in it, which we can model like this. And we'll call this the damping from the load, the inertia from the load. This is our output position, theta 2. The number of teeth on the first shaft is 100. I will say the number of teeth on the second shaft is 1,000. And we'll say that the motor inertia is 5 kilogram meter squared, and that the damping in the motor is 2 Newton meters per seconds per radian. And then we'll say first that we get KT and KV, and so let's say that we did a test here, and we found that 500 is the no load, is the stall torque for this motor, and that 50 is our omega no load. Of course, this is omega, and this is the torque for the motor. And so what we say is KT over RA is equal to our stall torque over our applied voltage, EA. So we'll say in this case that the applied voltage is 100 volts. And so we could say that this is equal to 500 Newton meters per 100 volts, or that KT over RA is equal to 5 Newton meters per volt. And then down here, this is our KB, and we'll say that the KB is equal to our applied voltage, which in this case is 100 volts DC, and at 100 volts we got 50 radians per second. So we get 100 over 50 radians per second, which gives us 2 volt seconds per radian. Okay, so we did some testing on the motor without the load and found our torque constants. And then we can just go back and do our modeling, which is theta m of S, which is the output of the motor dynamics over the applied voltage. So the output over the input is KT over RA quantity times JM. And we'll see here in a second that JM can be replaced with JE once we get the equivalent inertia from this system. Okay, and this is equal to S times S plus 1 over JM times DM plus KT KB over RA. Okay, and again, we can replace the JM and the DMs with JM, and DE can replace DM. I'll show you how we do that. And we'll come up with exactly the same equation. Okay. So we saw earlier when we have these loads attached to a motor that we can say that the motor dynamics, or the sum of applied torques, is equal to, the impedances of the shaft are equal to the sum of the applied torques. In this case, this is JM, which is the motor, plus JL, N1 over N2 squared. This quantity is times S squared. And this is plus DM, which is the motor damping, plus the motor load that we reflect on the destination shaft, times S, and we have this whole quantity times theta M of S. So these are our motor dynamics. And we can go back to our motor equation, which is, if the inductance is 0 RA over KT, TM plus KB S, theta M of S is equal to EA of S. And we can plug this in to this equation, and in that case we get RA over KT times JM plus JL N1 over N2 squared, that's our reflected inertia, times quantity S squared, plus DM plus DL N1 over N2, that's our reflected damping, times S. This is quantity S, and that's times theta M of S. So we just replaced this whole thing, went into this term here, and then we say plus KB S theta M of S is equal to EA of S. And so what we can do is just rename these terms. Okay, so we'll call this JE, we'll call this DE, our equivalent inertia and damping. So then we get an expression here, which is just RA over KT times JES squared plus DES times theta M of S plus KB S theta M of S equal to EA. And then we can just simplify this expression more and get JE S squared plus DE plus KBKT over RA times S theta m of s, and that's equal to EA of s, this is quantity of s, times KT over RA. And then we can, we want to normalize this by JE, so we'll divide both sides by JE. And if we do that, we can get this expression, which is S squared plus DE over JE plus KB KT over JERA times S times theta m of S, and that's equal to EA KT over JERA. And then we have, this is a function of S. Then we have our transfer function right there, because we've put everything that's in terms of the input and output. So we can say that our output over our input, which are functions of S, are just equal to KT over JERA times S, and then S plus 1 over JE DE plus KB KT over RA. And these are our motor dynamics. And if we go back and look at what we had before, you can see that the dynamics here are the same as the dynamics that we have here. But what we did is we took this whole connected portion, okay, and we reflected it, then replaced the JM terms from the motor with the JE terms and the DE terms with the DEM terms. And we got the exact same expression down here, where we have, instead of the JM here, we have JE, and instead of the DM, we have DE. Okay. So at the end of the day, if we plug our values in, we can say that JE is equal to JM plus N1 over N2 quantity squared JL, and this is equal to 5 plus 700, and let's make sure we put all of our numbers here. So in this case, JL is equal to 700 kilogram meter squared. DL is equal to 800 Newton meter per radian per second. And I think that's all of our numbers that we needed. Okay, so if we plug those in, then we put in that inertia, 700 times 100. N1 is 100. N2 is 1,000, so we have 0.1 squared, so it's 0.01. So this is just 5 plus 7, which is 12. And then we have DE, which is equal to 2, and that comes from here. This is 2 plus N1 over N2 squared DL, and that gives us 2 plus 800 over 0.01, which is equal to 10. Okay, so if we calculate those things, and we also saw before that our KT over RA, KT over RA was 5 Newton meters per volts, and KB said we have 100 over 50, which is 2 volt seconds per radian. And we can come in here and plug those values in. So we have theta M of S over EA of S is equal to 5 over 12 divided by S plus 1 over 12 times 10 plus 5 times 2. And that gives us 0.417 over S times S plus 1.667. Okay, so this took us through modeling of an electromechanical system, and we showed how we could take our motor dynamics from our circuit and couple those to the output torque. And a key equation here was that we have our circuit equation here. Okay, and in the circuit equation we have these current terms, and in a motor the torque is proportional to the current, and that allowed us to put our torque equation into the electrical system. We also know how to get the torque from the mechanical part of the system, and that's what we did here. We showed that, hey, this is the mechanical expression for torque, and so that allowed us to include the dynamics of the shaft into the electrical dynamics in the Laplace domain to get these expressions for a motor. And we said that, well, this is a relationship, and we have the electrical system and mechanical system. You see we have resistance and inertia and damping and our motor constants all in the same equation. We also showed how this expression, we could also use our equivalent inertias and damping when we have connected loads by reflecting them. And then we showed that, those reflected torques are the same. We also showed how we get our back EMF constants and our torque constants for a motor using the stall torque and the no load speeds for a given voltage. And then we put all that together in this example problem where we showed the dynamics between the input voltage and the output position of the motor on in this case, the first shaft.